This is a video answer key for the semester 2 test review, starting with balancing equations. We have a compound plus a compound makes a compound plus a compound, so that's a double displacement reaction. Balancing clue for this, look at your polyatomic ions and keep them together. Next one, we have an element plus a compound makes a compound plus element. That is a single displacement pattern. And for this one, maybe use the least common denominator method to balance it. Next one, we have two things coming together to produce one thing, or whenever two things come together or things come together to make something, that is a synthesis reaction. A specific pattern, when you have a carbon compound plus oxygen making carbon dioxide and water, that is a combustion reaction. And lastly, we have one thing breaking into pieces as a decomposition reaction. So anytime you see something breaking into smaller parts, that's decomposition. And those are pretty easy to balance. Next, we have our stoichiometry. I decided not to do the limiting reactant stoichiometry, so that was X'd out. First one is a one-step. How many moles of barium iodide are required to react with 3 moles of aluminum sulfate? So we start with the 3 moles of aluminum sulfate, and we want to know how many moles of barium iodide are produced. I'm going to put 3 on top, because that's what number's in front in the balanced equation. And I'll put 1 on the bottom, because that's what number is in front of our aluminum sulfate. So whatever's on the top here is on the bottom here, and vice versa. Whatever's on the top here is on the top over here. 3 times 3 gives you 9 moles of barium iodide. Now we go to a 3-step stoichiometry. So we have 13.4 grams of barium iodide. And then how many grams of aluminum iodide are produced? So first step is times 1 mole over a molar mass. Our second step, we look at our numbers in front in the balanced equation. Okay, so there's a 2 for the aluminum iodide. We put that on top because that's what we're solving for. Over 3 moles of barium iodide because there's a 3 there in the balanced equation. And we finish up with the molar mass of aluminum iodide per 1 mole. That mathematically is 13.4 divided by 391.1 times 2 over 3 times 407.7. That gives you 9.31 grams of aluminum iodide. Next, we do a little bit of nuclear chemistry. Okay, so this is a graph of a nuclear decay of iodine 125. How many protons and electrons does it have? Well, you go to the periodic table. Atomic number is 53, so that's our number of protons and electrons. To get neutrons, you subtract the 125 with the atomic mass minus the atomic number to get 72 neutrons. Okay, now let's look at the reaction that it goes through. It goes through positron emission. So we write the isotope 125 over 53, atomic mass over atomic number, and then the letter I goes to an arrow. And then we have this written first. Positron is E plus, and there's a 1 and a 0. Remember, the atomic number is on top, atomic number is on the bottom. And you've got these symbols all in your notes. The sum of atomic numbers on both sides must be the same, and so the atomic masses. So on the bottom, atomic number 1, and we need to get 53, so we know that this must be 52. 52 plus 1 gives me 53. Looking at the periodic table, element 52 is tellurium, element Te. 0 plus 125 gives us 125 over here. So that's tellurium, 125 over 52. What's the half-life for iodine? Well, the half-life, we go here, we start with 600. Divide that by 2, that means 300. We go over here, read down, that's 60 days. So it takes 60 days to go from 600 down to 300. So I'm going to record that as 60 days. Now, a related question, if we start with 500 instead of the 600 on the chart, how much would be left after 180 days? So I take 180 divided by 60, and I get 3 half-lives. So that means I got to take 500 divided by 2, and take that answer divided by 2, and then answer divided by 2. I will do that 3 times. Or I can just take 500 divided by 2 to the 3rd power, or 500 divided by 8 gives me 62.5. So that's our nuclear chemistry. Next, we'll do some empirical formulas and molecular formulas. So we have a compound here that's cholesterol. Okay, we have 83.87% carbon and a percent hydrogen and a percent oxygen all listed. Determine the empirical formula. Remember, we can treat those as grams because you could take a 100-gram sample. So we write each of their masses, okay, and that's their grams from our percentages. Now we divide each by the atomic mass from the periodic table, and that converts them to moles. And that's what each one of these numbers are. Then you divide the least into all of the largers, including itself. So 0.25 2.59 is the least. So dividing it by itself gives you 1. Divide this by that, 0.259 gives you 46. Remember, you round those. And then divide this by the 0.259, you get 27. Rounding each to whole numbers as long as they're close to whole numbers. So that means you got C27, H46, O. The next question, you have a compound with, again, percentages. You write all the percentages as grams. You want the empirical formula and also one extra step to get the molecular formula. Divide each by their atomic masses from the periodic table. And this time you get 1.29 for all of them. So you'll divide the least into all of them, which I guess themselves into each one of them. And that gets ones everywhere. So our empirical formula is O1, C1, N1, Cl1. We don't write ones. Now this extra step, here's our molar mass of the actual compound for the molecule, 232.41. So how do we handle that? So I'm going to do that down here so I have more space. We add up the atomic masses of each, 1 oxygen, 1 carbon, 1 nitrogen, and 1 chlorine, because each of those are ones in here. That turns out to be 77.5. Then you take that molecular mass provided, 232.41, divided by the 77.5 and get a whole number 3. So that means you take the initial and multiply it by 3, leaving you with O3, C3, N3, Cl3. So each one of those elements in the empirical gets multiplied by 3. Okay, and the last question for video 1 here, we're going to look at a hydrate formula. This one's a simulation for a hydrate of copper sulfate. You start the simulation, take the mass of your crucible, 42.22 grams, and then we add our hydrated copper sulfate, CuSO4 with water, and that is 47.22 when you're done with that. And then you heat your crucible, and then water is boiled away, and you're left with a dry copper sulfate and a final mass of 45.20. To get your grams of water, you're going to take 47.22 minus the final mass. So 47.22 minus our final mass, that gives you 2.02 grams of water. To get your copper sulfate left, you're going to take the final mass minus the empty crucible mass. So 45.20 minus 42.22 gives you 2.98 grams of copper sulfate. Now the next step in any empirical formula, of course, is getting in the moles. So I select the chart form for this. I'm taking my grams of water divided by the atomic mass of water. So that's 2 hydrogens and 1 oxygen, which is 18. I'll take my grams of copper sulfate divided by the molar mass of copper sulfate, so 159.6. Once I add 1 copper, 1 sulfur, and 4 oxygens together. That gives me my answers of 0.1122 and then 0.0187. We divide the least into all the largers. So I'm going to take that 0.0187, divide it by itself and get 1. And I'll take my moles of water and divide it by that and get the whole number 6. Remember, round to a whole number as long as it's close. So that means I got 6 amounts of water for 1 amount of copper sulfate. So then it's copper sulfate dot 6H20. This means there are 6 waters coordinated to 1 copper sulfate. And that's the empirical formula for it.